Hello everybody, thanks for taking the time to listen about nephelometers. I want to talk a little bit more about our 3 wavelengths integrating nephelometer Aurora 3000, and it's really 3 wavelengths and not 3 wave as it was in the announced. So it's called 3 wavelengths because it uses 3 different wavelengths of light. I will give you a little overview about nephelometer, talk a little bit about visibility, about the PM 2.5 measurements you can do with the nephelometer, and some climate research applications nephelometers allow you to do. The nephelometer itself is an instrument which measures the intensity of scattered light from an aerosol ensemble. And that's basically, you measure not only a single particle, you measure many particles which are in the measurement volume at the same time, in contrast to single particle counters which actually measure each individual particle. So with the nephelometer you get therefore integrated properties like the average, the mode diameter of your size distribution of particles, and the geometric mean standard deviations, stuff like that is basically part of the optical properties of a nephelometer. What influences the light when the light gets through the air? You have particles being able to scatter the light, and the amount of light scattered is depending on the particle sizes. If particles are very small or going down to molecules, you have basically the Rayleigh mode of scattering, which happens to be dominant when the particle sizes are less than 1/10 of the wavelengths you look at. And since the optical spectra has some different wavelengths, you will see that the scattering ability is higher for the shorter wavelengths. So with other words, the blue wavelengths get scattered more than the green or the red wavelengths. And that's basically the reason when you look at the sky and you see that the light coming from the sun, which is basically has an average size light spectra in the green, basically, that the blue lights part of the sun spectrum gets scattered down to you, and you see basically the sky blue. When particles get bigger, then you have another mode of scattering which can be described with the Mie theory, and the scattering there is basically such that most of the the light will be scattered in all directions, and therefore bigger particles scatter the light such that it appears to be at the same wavelength. So it's basically white light coming up and white light goes in when most of the light gets scattered. You can, in the most part, if you think you have very big particles like a mirror, then light gets basically mirrored and it gets in and out the same way. So that's described in the Mie regime. And when you look a little bit closer, then you will see that you have the incoming light to a particle. The particle kind of scatters the light in a given angle, and so you measure the incoming light here. The particle scatters, and you have a detector basically here, measures the intensity, and the intensity is dependent on the scattering angle, the wavelengths of the light, the diameter of the particles, the refractive index of the particles, and the imaginary part of the refractive index of the particle, so you have some absorption with it too. If you look at the angle behavior, you see a typical graph like that. When particles are very small, then the angle behavior is very smooth. It's basically flat behavior, and that's basically the signature of the Rayleigh scattering. So with the 17 nanometer diameter particles, you have a very flat behavior. If the particles get a little bigger, factor 10 bigger, then you have in the 170 nanometer, you see that it gets a little bit to backward angles, a little bit less scattering than to forward angles. So you get but it's still smooth. When you get bigger particles to 1.7 micrometer, then all of a sudden you get the Mie resonances of the scattering, which is dependent on the particle size, and you see a typical behavior like that resonance behavior, and a strong forward peak of the scattering. The note also on the scale, the bigger particles scatter much more. It's a factor 10 to power 3 suppressed to get it on the same scale. The 170 nanometer particle is the scale here, and the small particles are factor power 10 6 less. So that's basically how the scattering intensity would work. If you now start measuring, then you can do it in different ways. You can define different instrument for different application, and basically where your detector is sitting and you measure. If you have a detector measuring this angle area, then you measure the forward scattering area. If you have a detector sitting right at 90 degrees, you measure basically 90 degrees with a nephelometer, or in the backward area. And you will look around and find different nephelometers around on the market which have basically different areas, and then you measure a specific section of that function here. The problem here is basically that these resonances change with diameter. So next, if it's 1.8 for instance, then you might have a maximum here and a minimum here. So that's basically a highly dynamic measurement, what you see there. So the idea is to really measure the whole scattering angle area, and that's basically what an integrating nephelometer does. When you look into measuring the whole scattering angle, then there is one way you can do that. And here it's basically shown what you do when you want to measure the whole angle area. You have a light source basically here illuminating a particle loaded area, and the cone basically is the light cone. You measure the light exiting the light source in an angle like that, hits a particle here, the light gets scattered towards the detector, and so you have a scattering angle which is basically a backward scattering from here to here. A light going into the forward direction hits a particle here, gets scattered in that area, measured here, and you have a smaller angle scattering, a forward angle scattering, and all gets measured with the photomultiplier. The beauty of that system is that you basically measure the absorption exponent for the scattering in one shot, and this extinction coefficient consists out of the scattering coefficient and the absorption in there. The design basically is made in a way that the light, if the light source you use produces a cosine intensity profile, then you can actually measure the intensity like with that formula here. And for the full angle area, this represents basically 2p times the scattering coefficient, and so the outcome of an integrating nephelometer gets you basically the scattering coefficient, a constant, the measurement result, and the intensity of your light source in relation to it. And this result is very straightforward, a result which you can obtain with a integrating nephelometer. Have in mind, when you not integrate, then you have a little bit more work to do and to see that you're not stuck in any resonances there. The applications of a nephelometer is basically you can use the visibility. You can use it for measuring 2.5, sunstorms, brush fire. I will show you a little bit about the applications now. One application, visibility, is relatively obvious. When you look at the picture, on a clear day, you can see the mountains in the second row very easy here. When you experience a hazy day, then you see basically just slightly the front row mountains here, but the other ones are vanished. With other words, you have so much the light from the mountain area here doesn't make it through the air. It gets absorbed and scattered. And Goldschmieder developed the formula, which is basically the visibility length is that number divided through that extinction coefficient, where the visual range is basically in kilometers and the extinction coefficient is in megameters. As an example, when you're measuring 200 megameters extinction or scattering, then you have about a visibility of 19.6 kilometers or 12.2 miles. If you have a 2,500 megameters, then you'd be roughly at a mile visibility. So that's how you can basically define the visibility measurement. You need to know that basically when particles get measured in the free air, they are influenced by humidity. Particles in the atmosphere tend to grow with humidity, and you see here some measurements done at the Global Aerosol Watch Station in the Jungfraujoch in Switzerland. They measured the growth factor for different size aerosols with relative humidity. And you see that the particles with relative humidity grow almost 60% in diameter by just going from 10% relative humidity to 90% humidity. Of course, the diameter of the particle influences the scattering, and therefore when you want to measure the true visibility, you need to measure in the wet mode. That means you need to take the ambient conditions into account. You all know that when you measure PM, that there is a standard definition where you sample at a given, or where your samples get evaluated at a given relative humidity, and for that it is better to operate a nephelometer in the so-called dry mode, and the World Meteorological Organization recommends dry has to be less than 40% RH. You can do a lot of applications with a nephelometer. Everything else you can do with a normal mass monitor, and here you get basically a little idea from a brush fire in Australia. In this case, it was measured at different stations, and you had visibilities of less than 250 meters in that case, and comparable TIO monitor at that stage had that high mass concentration that the TIO filter needed to be changed every 3 days. So that's basically give you an idea of the range a nephelometer measures. And here you see a typical setup at a roadside station. You have basically a housing where the nephelometer sits. You can it's basically placed inside that housing here. It's not especially insulated because it would measure at ambient conditions, but it has also the possibility to heat itself, so that you can get the dry mode. The aerosol comes into that down tube here in the instrument. The down tube extends up to here to be at the same height as the other sampling probes. When you measure that nephelometer now in the dry mode, as I explained before, then you can compare that with, for instance, with an FEM beta monitor, which I did here. And you see the black curve is the FEM concentration, PM2.5, and the red dots are the measured scattering coefficients from the nephelometer, just divided by a constant factor of about a factor of 5 divided. And you see they track each other for a 2 weeks period very, very nicely. The green dots here represent the hourly relation, the scattered, basically the factor scattering divided by the equivalence method, and you see that the factor changes, but you see also the error bars, which I will explain later a little bit more in detail. When you plot the FEM versus the scatter coefficient, then you see that with that factor 5.2 I said, they correlate already pretty well within hourly numbers. So that shows the ability of measuring pretty neat 2.5 with a nephelometer. And when you go a little bit closer, I told you before that the particles grow with relative humidity, and when I wanted to test basically on that setup whether I have particle growth at that site. So what we basically did is I plotted the ambient RH against the scattering coefficient, or the ratio between scattering coefficient and FEM, and when I would have expected a particle growth, then the scattering should have getting bigger and bigger, and it doesn't really see more an increase of the thing, so there's no growth, and that's basically a good thing on the dry measurement. The error bars you saw in that picture are basically caused by the used federal equivalence method, and I looked into the data from the federal equivalence method and calculated the error trumpet for that, and you see that it is basically caused by the error from the federal equivalence method, and the ratios you gain here are basically filling that allowed space pretty well. And you see also when you have concentrations less than 50 or maybe 40 microgram per cubic meter, then the ratio can, just looking at ratios can be very deceptive, and you might think you need to calibrate your nephelometer, but it's more or less an error possibility there. This was basically a single wavelength nephelometer used here, but what is now an advantage of multiple wavelengths? When you use multiple wavelengths, then you have basically a chance to see different particle characteristics, because the blue wavelengths interact a little bit better with fine and ultrafine particles, so wood fires, automobiles react a little bit more with the blue wavelengths. The green wavelengths is throughout the visibility, so that's typically when you measure visibility, you measure in the maximum of the solar spectrum, and that's where the green measurement comes into play. And when particles get bigger, then the red wavelengths is a better choice, because you can get therein. But the three wavelengths gives you basically everything at the same time. And here you see an example of that roadside measurement where you see the three scattering coefficients basically measured at the same time over a period of time. When you look closely, you see that the trend looks pretty much the same, but sometimes the red is much less than the blue, and at other places the red and the green is a little bit higher than the blue even. So indicating that there is some changing there. With that said, you can to define a quantity which is called angstrom exponent. And this angstrom exponent expresses the spectral dependence of the aerosol optical depths as from the wavelengths as an inverse power law. So the scattering coefficient is proportional to the wavelengths power the angstrom exponent. The angstrom exponent can be obtained from a two wavelengths measurement simply by the logarithm of the scattering coefficient of the one wavelength minus the other divided by the wavelength difference. That's basically possible to get very easy with a nephelometer. And the good news is that for a particle size distribution, this angstrom exponent is actually inversely related to the average size of the aerosol particles, which we measured right at that inside the nephelometer. So smaller particles have the larger exponent, and that will be shown in the next couple of pictures, where I did take a section of the red scattering coefficient and plotted it against the green scattering angstrom exponent. And you see, remember, high angstrom exponents be small particles, and low angstrom exponents are bigger particles. So you have a very neat way to just plot that in a time series and see very nice changes during day-night. So this is at nighttime. Typically, particles get smaller in that thing, and then the angstrom exponent gets bigger. During daytime, it gets angstrom gets smaller, particles get bigger again, and then at night again, larger angstrom gets smaller particles. So that gives you a little trend, and you can look into diurnal patterns, and you can see whether particles grow during the day and see some more interesting parts. That's one application you can do with that angstrom exponent. When you look basically at a site like the roadside here, which we had done the measurement, you can see basically now in a windrows plot that the road here produces the higher concentration, because all of the concentration numbers in that angle area are higher than from the other side, where you have mostly some trees around there. And the prevailing wind direction you see basically in the blue curve over that time frame. That was about 3 months time frame. And what you also can see is that the angstrom exponent in green here is smaller from the road as from the other side. So with other words, the particles coming from the road are bigger than, have the higher concentration and are bigger than the particles coming from the other side to the side. So this is an information you wouldn't have been able to obtain by just measuring the concentration. You can look even a little bit more in detail, and that shows you how high dynamic you have with a nephelometer. These are 5-minute average numbers, and you see very nicely the scattering coefficient again. And in that episode here, you have very high concentration or higher concentration levels, and the angstrom exponent drops down considerably to here, which you can see is in the peaks even correlated with drops in the angstrom exponent. So now the question is, where is it coming from? What is it? As we know already, it's bigger particles because the angstrom exponent drops down. So what you can do now, you can do also a windrows plot for that time frame, and look a little bit closer to it. And what you see when you do that is that the wind, at this time frame, the wind direction was basically along the road, but you see the high concentration here comes from this side. And corresponding to that high concentration level, you see that dip in the angstrom exponent right in that angle area. So with other words, the big particles coming from that side, and now you know at least it's coming from that side. When you zoom in a little bit more, then all of a sudden you see, oh, look, here is some construction work going on, and that construction work is most likely the culprit of your bigger particles, which had been transported towards to that. And that was also, that effect was during daytime, so most likely there are some trucks had been on the road, and the angstrom exponent helps you to really to say that bigger particles came from that area. So I hope I showed you that there is some, the angstrom exponent gives you really a couple extra information. You get something like the aerosol dynamics. You get indicates of changing aerosol mix. You have a new way of source apportionment, because you can now say I want only looking for particles with that type of angstrom exponent and look for where they're coming from. They are easier than spectral measurements, because you can just calculate them and run them like a regular time plot, and you just look at them. The diurnal patterns can be looked at, particle growth episodes, and there is even a possible particle classification install. The next picture shows you a plot of the extinction angstrom exponent versus the absorption angstrom exponent, and these two measurements had allowed the AeroNet data, which are taken in several places around the US, were measured, and you could take a classification for different kinds of dust. So, for instance, biomass burning would land in that area of that plot. Urban industrial dust concentrations would come from this area. Desert dust, long-range transport in that area. So you see, there is a chance to dissolve what kind of dust you have by just measuring the scattering and the absorption angstrom exponent. But that's not all you can. So I guess I showed you the angstrom exponent has quite a few applications when you measure that with a integrating nephelometer, and to do that you really need a two wavelengths integrating nephelometer, and also for the absorption angstrom exponent you would need a two wavelengths SLometer or photoacoustic instrument to get the absorption of black carbon in that area. The other thing you can measure is the aerosol asymmetry parameter. I showed you at the beginning that when the particles get bigger, that the aerosol scattering has a forward peak, and you get more forward than backward scattering, and that can be described as the aerosol asymmetry parameter. You can measure the single scattering albedo, and for all of that you need multiple wavelengths instruments. When you want to answer questions about global warming, then you want to make sure that what is the contribution of particles to the global warming trend, and nephelometers will be used to help answering that kind of question. As mentioned earlier, the forward and backward scattering of particles when you go into gas molecules and small particles have been basically forward and backward the same, while large particles have more forward scattering. And that would lead to a situation where if you have basically particles in the atmosphere, that the sunlight hits the particle, scatters the particle outside, and if more particles get scattered in this outside direction, it actually cools the air, and if more particles get scattered down, then it actually heats the planet, and that's part of why you need to know whether the particles do more backscatter or more forward scatter. So the Aurora 2000 has a backscatter option, and you can measure the scattered light towards the backscattering hemisphere and the forward scattering to help answer these questions. And how this is really done is basically you measure the light as light from the particle-loaded air here, but you include a shutter which blocks the forward part of the scattering so that only light going in the backward side reaches the detector, and then you measure one time without that shutter and one time with the shutter, and then you have forward scattering and total scattering, and then you have basically the range from 90 to 180 degree measured, and that gives you the asymmetry parameters there. In practice, we have a very nice little mechanics doing that. You see that how it's done with that little motor where you shield the light source towards the photomultiplier area here in this direction now, and that's basically how that backscatter works. The other parameter you can measure with the nephelometer, which is basically an important parameter for the global warming effects, is the measurement of the single scattering albedo of the aerosol. And as I showed you earlier, the extinction needed is the scattering coefficient and the absorption coefficient. And the single scattering albedo is basically the scattering divided by the extinction, and it's typically basically a value between 0 and 1, because the extinction is scattering plus absorption. So this is the single scattering albedo, and of course you need to measure scattering and absorption out of these three quantities to define that single scattering albedo. When you look at, for instance, wildfires, you see influences of single scattering albedo. You see a typical behavior that the dust here is all black. When you have an oil fire, it's pretty much black dust, and that is caused by a lot of black carbon in there because you have a high absorption there. And if you have a high scattering area, that you get a white cloud, you have a higher albedo because the scattering is more dominant into that area. So when you look into aerosols in the atmosphere, you have 5 basic components, 5 main components. That's the organic components, sulfates, nitrates, and some soil and elementary carbon, where the only absorber to it is the elementary carbon. And so the more carbon you have, the more absorption you have, the smaller the single scattering albedo gets, and then you get more, get a higher effect on that. And if the absorption gets bigger, then of course the single scattering albedo gets smaller. And aerosols contribute to the heating if they are darker than the surface below. Then that means that the single scattering albedos of the particles in the air is less than the surface albedo, meaning that the underlying surface of the air reflects some light also, and if that reflection is less than that single scattering albedo, then the particles basically heat the Earth, and if you have a more scattering, as I explained earlier, then you will cool the Earth down. So that's basically the models you do to define what is the effect of aerosols in the atmosphere. In reality, it's a little bit more complex because to even single-dimensional radiative transfer models need to involve also the asymmetric parameter or the hemispheric upscatter fraction, and taking multiple scattering and reflection into account, not only a single, as I had explained in the course of that. Furthermore, when you have your aerosol in the air and your black carbon aerosol absorbs it, it gets warmer, but once imagine that aerosol drops on a snow field and makes it darker, then all of a sudden it changes the surface of the it changes reflection from the surface and changes it. So there is a lot of complex issues, and that's why the researchers have not a really clear answer on it, but at least you need to get the individual contributions, and nephelometers help you to answer these individual contributions. If you use that single scattering albedo values in the plot I showed you earlier, the researchers now go actually further along, and you have the scattering absorption exponent here, and the absorption exponent in this area multiplied with the single scattering albedos, or a differential single scattering albedos, then they are basically able to make a better discrimination of different particle modes, and this shows a model calculation for different modes where you can distinguish in that, and that can be even future applications of nephelometers, because you can distinguish different particle groups. So I hope I showed you that nephelometers are really versatile tools. We can use them for global warming trends, for aerosol growth function, visibilities, PM correlation, wildfire, smoke, and haze measurements. And so that's basically all I wanted to tell you about the nephelometer at that time. And you're more than welcome to ask a couple questions and get into our moderator there. Thank you very much for your attention, and it was good that you thank you that you took the time to listen to that.
Okay, Herbert, thank you very much. It's Andres here again from American Ecotech. I was here with Joe Colombo. Thank you so much for your time today. I've just muted Herbert momentarily so we don't get so much feedback on the line. But yeah, we do have a couple of questions, Herbert, and I'll repeat the question. I hope you can actually answer it. If not, I'll help you answer it. Otherwise, we will be answering all these questions by email. If you have any particular questions that you want to send them now through the GoToMeeting chat. Also, there was a question regarding the presentation being available afterwards. We will have a recording of this presentation available for everyone that attended. So you should receive a recording of it over the next 24 hours or so. So just keep that in mind. Now, Herbert, the question that we got was regarding the normalization and the effect of the pressure in like ambient temperature and pressure in the actual readings, and do you need to normalize your readings or you don't? I'm not sure. Can you help us answering that question?
Yes, there was a question about normalizing the nephelometer measurements. As I explained, the scattering is dependent on the number of scatterers, and the number of scatterers is dependent on the number of particles in that area. And of course, if you have ambient conditions, then the number of scatterers are basically dependent on the volume you have. So you have a volume-dependent correction in there, but the nephelometer itself measures the temperature and the pressure inside, so it will give you the corrected numbers for that. So that's basically what it is, but it is measures. It measures the scattering at ambient conditions, and so that's what you need to look at.
Okay, thank you. Yeah, I think that was that question. Otherwise, if there are no other questions coming through, thank you very much for everyone that attended today the webinar. I certainly find it very informative. It's helped us identify, and there's a fair bit of work and research is gone into using different wavelength nephelometers to actually characterize the size of particles and getting a lot of information out of it, certainly. So not being any more at the moment, I think we leave it like that, and then we'll be once again, we will be able to post this recording webinar within the next 24 hours, so you guys all will see it. So thank you everyone for attending, and thank you, Herbert.